Okay. Okay, so this is going to provide a general review for the topics for this first exam. So this is covering a review of undergrad reactor design. And so our starting point for a lot of these reactor design problems is going to be general mole balance. And so for some arbitrary species J, we can write a mole balance as a molar flow rate of J going into the reactor volume minus a molar flow rate of J leaving the reactor, plus a rate of generation of J within the reactor volume. So for generality, this can be an integral over the reactor volume, so we can have spatially distinct reaction rates based on differences in temperature or concentration at different points in the reactor. And this is going to be equal to the accumulation of number of moles of J with time in the reactor volume. So we can have different simplifications for our three different types of idealized reactors. So the first one is the batch stirred tank reactor, or simply batch reactor. And this we assume is a closed vessel with no flow in or out. And we generally say that it's well mixed. So because of this, we have no flow rate terms in or out of the reactor. And we usually say it's spatially uniform, so the integral of the reaction rate with respect to volume can be written as just the product of the reactor volume times the reaction rate. So our mole balance becomes this differential equation. And if we have constant volume, so this could be the case if we have, say, a gas phase reaction where the reactor volume dictates the volume of reacting fluid, or if we have a liquid phase reaction with constant density. So if that's the case, we can write the number of moles as the concentration times the volume. So in the case that the volume's not changing with time, we can pull it out of this time derivative and cancel it out with the volume on the other side, giving us this simplified differential equation here. So this is for constant volume. Okay, so our second idealized reactor is the tubular reactor or the plug flow reactor. So this often looks like a cylindrical pipe where we have flow going in and flow coming out. And here the assumption is that the fluid travels as a plug through the reactor. So there's no axial mixing along the length of the reactor, but things are well mixed sort of radially at a certain cross section along the reactor length. So here the differential equation that describes the molar flow rate of some species J throughout the reactor volume is just the this derivative is equal to the rate of generation of that species J. So this is for a steady state tubular reactor. Okay, so if it is constant density, and constant density means that the volumetric flow rate at any point in the reactor is equal to the inlet volumetric flow rate, then we can simplify this differential equation to write the change in concentration with resonance time tau is equal to R of J. So here the resonance time tau is equal to the reactor volume divided by the inlet volumetric flow rate. So you can see clear similarities between the differential equation for the batch reactor and the plug flow reactor, with the tubular reactor having the resonance time tau taking the place of time in the batch reactor. So finally, we have the continuous stirred tank reactor. So this looks like a tank where we have flow terms coming in and out. And this is operated at steady state and is well mixed. So this means that the concentration of species J are the same everywhere in the reactor and same as the conditions of the reactor outlet. So the general mole balance for the continuous stirred tank reactor is now an algebraic equation rather than a differential equation. And if it's constant density, so we have a constant volumetric flow rate, and we can write this in terms of concentration and our residence time, tau. Okay, so another useful term in designing reactors is the conversion. So we can define the conversion of some species A as the number of moles of A reacted divided by the number of moles of A fed. So this is a way to track sort of progress of the reaction. So you always need a basis of calculation, and be careful of using conversion when you have multiple reactions involved, since each one of these reactions has their own conversion. So we can rewrite the mole balances in terms of conversion. So for our batch reactor, here we can define the number of moles at any time t as the inlet number of moles minus the inlet number of moles times the conversion x. So this is just how many we feed minus how many reacted. So with that in mind, we can rewrite the mole balance. So it's going to look something like this, where now we can replace this expression for the number of moles J at any time. So this is going to be time derivative of Nj naught minus Nj naught times X dt. And so this just comes out to minus Nj naught dx dt. So the change in conversion time. For the CSTR, here we're going to rewrite the molar flow rate of A at any residence time in terms of conversion. So this is the molar flow rate in minus molar flow rate in times conversion. So doing this, we can rewrite our sort of general mole balance for some species J. So this is the molar flow rate coming in minus the molar flow rate leaving the reactor. So that's going to be Fj naught plus Fj naught times X. So these terms will cancel. Plus the rate of generation of that species J is equal to 0. And oftentimes we will solve this for the reactor volume. So in that form, the reactor volume is going to be Fj naught times the conversion divided by the rate of consumption of that species J. Okay, so finally for the plug flow reactor, we had this differential equation as our mole balance for species J. And so here we can use this expression to replace the molar flow rate of species J with conversion. And if we do so, now we have a differential equation that looks like this. So Fj naught times dx dv is equal to the rate of consumption J. Okay, so the next thing we discussed in the class was stoichiometry. So sometimes there's changes in number of moles with reaction. So this can result in more complicated relationships between concentration and conversion. And a stoichiometric table is generally helpful for keeping track of these things. So we can look at this with an example. So here we'll have a non-constant density batch reactor. So let's say we have this reaction 2A plus 3B reversibly going to 5C plus D. And it's fed with some inlet concentration or inlet number of moles initially charged with A and B. Okay, so we can write a stoichiometric table here using A as a basis. So here we keep track of our species, A, B, C, and D, and how much we have initially, how much it changes in terms of conversion with reaction, and then how much we have at the end or at some later time t. So we start with a batch reactor that's charged with some number of moles of A and B, and initially we have no C and D. And for A, we have a change in number of moles of minus Na naught times X. That's just the number of moles of A reacted is equal to the number of moles of A fed times the ratio of the number of moles reacted per mole of A fed, which is the definition of conversion. For our species B, we have minus 3/2 Na naught times X, since for every 2 moles of A that react, 3 moles of B react. And then for our products, we have positive change. So we have 5/2 Na naught times X for C, and 1/2 Na naught times X for D, since these are formed in stoichiometries of 5 to 2 for C and 1 to 2 for D. So now we have expressions for all of our terms, all in terms of conversion of A. So our species A will have Na naught times 1 minus X moles at any time T. For B, we'll have NB naught minus 3/2 Na naught times X. For C, it'll just be plus 5/2 Na naught X. And for D, we'll have positive 1/2 Na naught times X. Okay, so with this, we could, for example, find the equilibrium conversion given some information about the reaction thermodynamics. So let's do this as an example. So we could find the equilibrium conversion at 298. Kelvin, if we're given the standard free energy of reaction, it's equal to minus 10 kilojoules per mole. And we can assume that Na naught is equal to Nb naught, and that we have a constant volume liquid phase reaction with all species at unit activity. So here, the equilibrium constant we can write as the concentration of each species to their stoichiometric coefficients. So Cc to the 5th, Cd to the 1st power, divided by the concentration of reactants to their stoichiometric coefficients. So now we have equations for all of these in terms of conversion. So since it's constant volume, we can write these in terms of concentration. And this is going to be equal to the equilibrium constant, which is equal to e to the minus delta G of reaction over RT. And so here we could use this information to solve for the equilibrium conversion XA. Okay, so oftentimes it's useful to combine reactors, either in series or parallel. And so if we have, first let's talk about the plug flow reactors series. So if we had, say, two reactors in series, with, say, Ca1 going into the first reactor, here we'll say that the residence time is equal to 0. This first reactor has a residence time tau1. And here we have a residence time tau2 for the second reactor. So here, leaving second reactor, we're at a residence time of tau1 plus tau2. So we can write a mole balance on the first reactor. So dCA d tau is equal to parse of A. So let's say it's a first order reaction. So the rate of generation of A, if it's a reactant, is minus kCa. So we can integrate this expression, separate and integrate this expression. So we have from tau equals 0 to tau equals tau1 minus k d tau on one side, and our integral for the concentration is going to be dCA over Ca, and we'll integrate this from, say, a position Ca0 entering the first reactor to a concentration Ca1 leaving that first reactor and going into the second one. So we get an expression that looks like this. So Ca1 is equal to Ca0 times e to the minus k times tau1. And we can do a mole balance then on the second reactor. So this is going to look quite similar, where the concentration of A leaving the second reactor is going to be equal to Ca1 times e to the minus k times tau2, or Ca0 times e to the minus k times the sum of the two residence times of the two reactors. So this is exactly what we would get for the expression where we had one tubular reactor that's twice as long. So essentially what we get when we have two tubular reactors in series is the sum, or the expression that you would have for one tubular reactor with a resonance time equal to the sum of two reactors. So really there's no difference here of having just one longer reactor or two reactors in series. Okay, so what about for the CSTRs? Okay, so let's say we have some setup that looks like this. So here, let's say we have a concentration Ca0 going into the first reactor, concentration Ca1 leaving the first reactor going into the second one, and a concentration Ca2 leaving the second reactor. We have some resonance times, tau1 and tau2 for our two reactors. Okay, so if we do a mole balance on our first reactor, and again, here we'll say this is a first order reaction. So we can write Ca0 minus Ca1. So that's the concentration leaving the first reactor. It's equal to R of A minus R of A times tau. So since this is a first order reaction, we can just write it as K times the concentration of A in the first reactor, and it's equal to the concentration in the outlet of the first reactor, Ca1, times tau. Okay, so we can solve this for Ca1 as a function of Ca0, K, and tau. We do this, it comes out to concentration of A leaving the first reactor is equal to the inlet concentration divided by 1 plus K times tau1. Okay, so then we can do a similar mole balance on the second reactor. So we have now Ca1 as our inlet concentration, Ca2 as our outlet concentration, and this is again equal to the rate of consumption of A times tau. But here the rate is evaluated at the conditions of the second reactor, so that's equal to K Ca2 times tau. And so again, this tau is tau2 for the second reactor. Okay, so solving this for Ca2, we get this is equal to Ca1 divided by 1 plus K tau2. So this is an expression that looks very similar to the one that we got for the first reactor. So we can plug this expression in for Ca1 to get this all in terms of Ca naught. So this is equal to Ca naught divided by 1 plus K tau 1 times 1 plus K tau 2. So we have in the denominator the product of these two terms that describe the residence times for the first and second reactor. So here you can see that the order is not important. So if we put the first reactor, this tau 1 first or second, so just flip the order of the two, we would still get the same expression where we have this product term in the denominator. So here we have no preference for order of the reaction. Unlike the plug flow reactor, we do get different conversion. If we had just one larger CSTR, the conversion we would get for a first order reaction would be smaller, but the order of reactors is not important. And so for a first order reaction, we can actually generalize this for n reactors. This is going to be equal to Ca naught divided by the product from I equals 1 to n for our n reactors of 1 plus K. So we can assume, say, that this is isothermal, so the reaction rate constant is going to be the same in all of our reactors, tau times tau I, and this is to the I. Okay. So what about when we combine what if we have combinations of CSTRs and PFRs in series? So the general rule here is that if the reaction order is greater than 1, you want to basically delay the mixing as long as possible to keep the reaction concentrations high and maximize rate. So for a second order reaction, say, it would be advantageous to have a PFR first before the CSTR, because the plug flow reactor, the concentration is steadily dropping along the length of the reactor, whereas for the CSTR, the reactant is immediately diluted to the outlet concentrations. So here you would have higher conversion. This again for a second order reaction than if you had the CSTR first for the same reactors. Okay, and so this is dependent on the reaction order. So if it's exactly equal to 1, the ordering of the two reactors does not matter. And if the order of the reactants is less than 1, then the opposite is true. You want to have the mixing happen earlier. Okay, and so you showed in the problem set mathematically how you can get the how you can demonstrate that the order doesn't matter if you have first order reaction. So in that case, you would get equivalent mathematical expressions for the concentration leaving the reactors if you put the PFR first or the CSTR first. Okay, so one graphical representation, sort of visualization of these reactor design problems that's very useful is the Levenspiel plot. So you can see what the Levenspiel plot is demonstrating by looking back at the mole balance. So if we write the mole balance for a PFR in terms of conversion, looks like this. And so if we solve this out in integral form for the reactor volume, this is an integral of FA naught divided by minus RA dx. And so we can see the similarity with the CSTR. We solve out that mole balance for volume. So this is equal to, so the volume is equal to FA naught divided by minus RA times X. Okay, so here if I plot FA naught divided by minus RA as my y-axis and conversion as my x-axis, then the reactor volume you can see is going to be an area of a rectangle of dimensions y times x for a CSTR. And for the plug flow reactor, it's going to be the area under the curve from 0 to x. You can see those limits of integration being 0 to x. Okay, so here, let's draw one of these Levenspiel plots. So we have, again, FA naught over minus RA as the y-axis and conversion as the x-axis. So I'll draw this, say, for a positive order reaction. So the shape here depends on the rate expression. So here, why we have this sort of positive slope is because up here where we have high conversion, the reaction rate is going to be small because all the reactant is basically depleted. And here where we have the highest concentration of reactant, we're going to have the highest reaction rate. So here, for some specific conversion, call this X1, this is the volume needed to achieve that conversion for a plug flow reactor. And the area of this entire rectangle would be the volume needed for a CSTR. So you can see here that the volume is significantly larger for a CSTR than for the PFR. And this is generally true if we have a positive. So you can also see that with a large number of CSTRs, say if I had same sort of Levenspiel plot, and instead of using one CSTR to get to some conversion X1, I used a number of CSTRs. So the volume might look something like this. You can see that with more and more CSTRs, the volume starts to approach that of a plug flow reactor. So all of these little rectangles together start to approach the area under the curve if we make enough of them. And so essentially what this is saying is that you have many, many CSTRs in series. This approximates the performance of one plug flow reactor. And so physically why this makes sense is because the CSTR essentially has well-mixed fluid. And so you can think of these small CSTRs as differential cross-sections along the length of that tubular reactor. So we could call these, say, 1, 2, 3, 4. These would be different positions. Clean this up for clarity. These would be different positions along the length of the reactor, 1, 2, 3, 4, right? These are well mixed. Okay. So sometimes we can have different shapes to our Levensspiel plot, and it can very easily give us some insights about what's going to yield the highest conversion for a given reactor volume, or if we have a desired conversion, what might be the smallest reactor we could use to achieve that. So if we have, for example, something like an autocatalytic reaction, which has a very different shape to that Levensspiel plot, it might be advantageous to use different types of reactors for different specified conversion. So if we wanted to be at some conversion x1, here actually it would be advantageous to use a CSTR. So that would be the volume needed for a CSTR. And you can see that here the area in the curve under the curve, so the volume needed for a plug flow reactor is actually higher. But if we wanted to go to a much higher conversion, just do this in a different color, x2, here the area of that rectangle for the CSTR is significantly larger than the area under the curve. So you have all this extra volume for the CSTR relative to the PFR. Okay. So the next thing we talked about in the course was having multiple reactions. So sort of an idealization that we have single reactions, and in any sort of practical system, we're going to have more than one reaction. And so when we have multiple reactions, the important point is not just maximizing the conversion or the productivity to one product, but modifying the selectivity, so modifying the relative rates of these different reactions. So we can have different types of reaction networks for multiple reactions. These could be reactions in series. So you have A going to B, but then B can subsequently react to form a secondary product C. You can have parallel reactions. So A going to form one product, then forming other products that may or may not be desired. And then we can have combinations of this, both types of reactions. So say A plus B go to C, C, B plus D reacts to form E. Excuse me. So we can have B plus C reacting to form D. So this is in series from the perspective of C, but in parallel from the perspective of B. And so you can have different types of networks that combine series and parallel reactions, and this sort of captures the main essence of even very complicated types of reactive networks. So writing the mole balances in these cases just requires accounting for all the different ways that the species is formed and consumed. So let's say, for some example, if we have A plus B reversibly reacting with rate constants K1, K minus 1 to form C, and then we have a series pathway for C and a parallel pathway for A. Let's say that this one is irreversible with a rate constant K2, and this forms D. And then B and D react irreversibly with a rate constant K3 to form E. Well, we could write, say, in a plug flow reactor, mole balances on each one of our species. So if we wanted to do this, say, for A, so dFA dV is just going to be equal to the rate of formation of A. So that's going to be minus K1 Ca Cb if this is an elementary reaction. So that's because the forward reaction in this first equation consumes A plus K minus 1 times Cc, since the reverse reaction forms A, minus K2 times Ca Cc. So this second reaction consumes A as well. For B, we could write this equal to minus K1 Ca Cb, because that first reaction consumes B stoichiometrically, just like it consumes A. The reverse reaction, K-1 Cc, that produces B. And then we have a secondary pathway that consumes B as well, this third reaction. So that's going to reduce the molar flow rate of B with position in the reactor. And the rate of that is going to be dependent on the concentration of B, concentration of D. Okay, so here we have a coupled set of differential equations. So we can use different types of numerical differential equation solvers to get, say, the profiles of molar concentrations or molar flow rates versus position in the reactor for something like a tubular reactor, or how they change with time for say the number of moles change with time for a batch stirred tank reactor. Okay, so often there's a product of interest and an undesired pathway. And so we can think about how the different reaction rates in these multiple reactions depend on temperature or concentrations to determine what conditions we should use to run our reactors to maximize the selectivity. So let's look at an example of this. So if we have A plus B going in one pathway to form a desired product, the reaction rate constant K1. So the rate of consumption of A in this reaction is equal to K1 times Ca times Cb. And then there's a secondary pathway that forms an undesired product U. This has a different reaction rate constant. And let's say it has a different rate equation that depends on Cb squared. So we can write the selectivity, instantaneous selectivity of D relative to U. So this is the rate of formation of D divided by the rate of formation of U. And so this is going to be equal to KCA/Cb divided by K2 CA/Cb squared. So you can see that this depends on the relative rate constants for the two reactions. So this could depend on the temperature, since they'll have different activation energies, therefore different sensitivity to temperatures. And it's also going to depend on the inverse of the concentration of B. Okay, so here you can write out the Arrhenius type expressions for the rate constants. Okay, so let's say EA1 is greater than EA2. So the sensitivity to temperature of the first reaction is larger than for the second reaction. So this means that K1 will increase more rapidly than K2 when you increase temperature, and the reverse would be true. So K1 increases. So here we would want to operate at high temperature if we wanted to maximize the selectivity to D, and the reverse would be true if EA1 was less than EA2. So here, we want to operate at low T. And so in both cases, you can see that we want the concentration of B to be as low as possible if we want to maximize selectivity. So one potential option for doing this is we could have a semi-batch reactor filled with A, where B is fed over time. So this could look something like this, where we have a tank filled with A initially, and then B is fed over time. So it reacts very quickly once it's added to the reactor, so its concentration never gets too high. Okay. And yeah, like I mentioned, most systems involving multiple reactions cannot be solved analytically, since we have these coupled ODEs and require numerical methods. And we saw some examples of both cases. So we saw in the videos some simple expressions for, say, series reactions or parallel reactions where analytical solutions existed. But we also saw in the problem sets some examples where we could use Excel or Polymath or MATLAB to solve these systems numerically. Okay, so then the final topic we touched on in this unit was energy balances and heat effects. So before that, everything was kept isothermal, but non-isothermal conditions are very common in reacting systems because these reactions liberate or consume lots of heat. Think reactions like combustion, and they also depend very strongly on temperature. So the reaction rate constants and equilibrium constants depend strongly on temperature. And so we want to be able to solve non-isothermal problems to both, keep our reactor safe, but also do an effective job of designing reactors, since these heat effects are going to be very influential in determining reaction rates and changes in number of species with time and position of a reactor. So to solve non-isothermal problems, we can write an energy balance that we solve simultaneously with our mole balance. So in words, what this looks like is something like an accumulation of heat in reactor is equal to a heat flow in from the fluid. So how much, say, enthalpy the fluid carries in, a heat flow out by the fluid, an amount of heat generated by the reaction. So this depends on the enthalpy of reaction, plus the energy exchange or heat exchange with surroundings if we have no work done on the system. Okay, so say which terms are going to be zero. So this accumulation of heat is going to be zero for steady state systems. These flow terms, so fluid going in and out of our system, are going to be zero for our batch stirred tank reactor. And this heat exchange with surrounding is going to be zero for adiabatic systems. So if there's no exchange with the reactor environment. Okay, so for a batch stirred tank reactor, for example, this energy balance is going to look like reactor volume times the heat capacity per volume, rho Cp, times the change in temperature with time is equal to the reactor volume times minus delta H of reaction. So this is the times the reaction rate. So this is the amount of reaction happening is R times V, and then the heat released per reaction is delta H of reaction. So this is how much heat is being generated by reaction. And this is minus U times A times T minus TC. So this is the heat exchange with the surroundings, where you have an area available for heat transfer A, you have a heat transfer coefficient U, and then you have a driving force for heat transfer, this temperature gradient, T minus TC, where T is the temperature in the reactor, and TC is the temperature of the environment, say a cooling jacket. So here we have a differential equation with respect to time, since the batch reactor is not operated in steady state. Okay, for a CSTR, again, we're going to have an algebraic equation, and we're going to have no time derivatives since it operates in steady state. So this is going to be T minus T naught, so the temperature in the reactor minus that of the inlet fluid, is going to be equal to tau, the residence time, times, here we'll write this in the general case for multiple reactions. So if we have, say, R reactions, each one of those having a enthalpy of reaction This is divided by rho Cp, so that's the heat capacity per unit volume of the fluid, times RV, so that's the reaction rate for each one of those reactions. So this heat generated by reaction depends on the heat of reaction, the rate of the reaction, and the heat capacity of the fluid. So for a given amount of heat generated, how much does that actually raise the temperature of the fluid in the reactor? So here again, we're going to have a term associated with heat exchange with the exterior, and that's going to depend on the temperature within the reactor and the temperature of the sort of cooling fluid or exterior of the reactor. This also depends on the area available for heat transfer and the heat transfer coefficient, so how efficient that transfer of heat is between the reacting fluid and, say, the walls of the environment, or the walls of the reactor. Okay, and then finally we have, for a plug flow reactor, again, a differential equation, but here with respect to position in the reactor rather than say, time. And that's going to be dependent on the heat generated by reaction, the heat exchange between the reacting fluid and, say, the walls of the reactor, and the heat capacity of the fluid, which dictates how much the fluid heats up for a given amount of heat added or removed from the system. Okay, so here the temperature changes along the reactor length, and it's not a function of time. Okay, so again, here we're going to have a differential equation, a coupled set of differential equations. We'll have our mole balances and our energy balances that are solved simultaneously. So these are functions of the reaction rate. And then in our mole balances, say we'd have something that looks like this, where our reaction rate constants are temperature dependent, so those will couple to the energy balance. Okay, so let's look at a quick example. So if we have a gas phase reaction, A goes to B in an adiabatic PFR, it's first order. You can say minus R of A is equal to KCA. The reaction rate constant follows a Arrhenius type relationship with some activation energy. So let's say it's 20 kilojoules per mole. And we have delta H of reaction being equal to minus 60 kilojoules per mole. This is an exothermic reaction. And we might want to, say, plot the temperature, volumetric flow rate versus position in the reactor or residence time tau. Okay, so if we have our energy balance, dt dV is equal to minus delta H of reaction times R minus this term associated with heat exchange. So this is actually all going to be 0, since we said it's an adiabatic reactor. There's no heat exchange with the surroundings. And that's the heat capacity of the fluid. So since delta H of reaction is negative, this entire term is going to be positive. So we're going to have an increase in temperature with volume or with position along the reactor. So as tau increases or volume increases, the temperature is going to increase. So with what functional form? So will it increase linearly? Will it increase with a faster rate initially with respect to reactor volume? Accelerate with position? So here, as the temperature increases, that's going to increase the reaction rate. So that's going to generate ever more heat. So here, the rate of increase of temperature with position in the reactor is going to increase. So, our graph of temperature versus position or residence time in the reactor is going to sort of shoot up. So here, as the temperature increases, it increases the reaction rate, which further increases the temperature. So for this exothermic reaction, if it's not thermally controlled or limited in reactant, it could run away. So if there's nothing that stops this thermal increase, the temperature is going to just continue to increase exponentially until you get big problems. Okay, so the final thing I wanted to touch on here is heat effects for multiple reactions. So let's say if we had reactions A going to B and A going to C with rate equations that look like this, and some information about the activation energies and reaction thermodynamics. We could say, for example, if C is our desired product, we could ask the question of whether we should operate isothermally or adiabatically. Okay, so looking at these delta H's of reaction or enthalpies of reaction, if we operate adiabatically, the temperature will decrease. And so this reduces K2 more than K1, hurting the selectivity. So then you want to run this reactor isothermally. So this, just summarize this, reduces K2 more than K1, hurts selectivity to C. Okay. So with that, that sort of summarizes what we covered for this first unit. So we covered generally mole balances and reactor design for isothermal systems. First for single reactions, we did this in terms of concentrations or molar flow rates, as well as conversion. We then looked at reactors together in series or in parallel. We extended the analysis from single reactions to multiple reactions, thinking about how we could optimize selectivity with changing reactor design. And then finally, we looked at some temperature effects or heat effects and how we can solve reactor design problems in light of these non-isothermal effects, and also how we can design for selectivity when we have multiple reactions, taking these things into account. So hopefully that was a useful review of the topics that we covered and can kind of guide your studying as you prepare for this exam.